Hey guys, how's everything going? This is JSer. There is only 2 days before my interview. I plan to take a brief recap on the top Facebook questions. So here we go. There are only 50 of them. So let's start from let's sort them by frequency. So I'll go from top to bottom. The first one is trapping rainwater. Okay, I remember this one. So we're like some board. So how can we trap the water? So the idea is simple. Simple. For each point, the water it contributes like the point here it contributes is the maximum of left to the left and the maximum to the right, and choose the smaller one, right? The smaller of maximum of left and maximum of right. So we can actually we can brutally calculate them, but as we did at the subarray problem, we can cache them, right? So the max the max to the left for each point, and we loop through from right to left and cache the maximum to each point, and then we can just directly get the maximum and do the calculation. So it will be linear time. If we don't cache the sum, if we don't cache the maximum, we will start looping through the all the nodes to find the max, right? So it will cost us n square. The largest one, yeah. So that's it. Okay, that's the 42 trapping rainwater. The second one, merge case sorted list. We're going to merge this list. Well, the idea is there is a lot of implementations. Let's take a look at the solution. Well, what I did here is actually the last one. So the brute force. Okay, we collect all nodes and do the sort. Wow, it's very slow. Suppose there are n nodes, we need to sort them. It was O n log n, right? And a space O n. Cool. And then compare one by one. What does it mean? Get every k nodes the head and get the smallest. So we need to sort them, right? It says we don't sort. We just do the traversal for k nodes and find the smallest one, and there will be n nodes. Yeah, so yeah, get k nodes, find the smallest one, put it, and find the smallest one, put it. So this is a kn. Yeah, space complexity, it's linear time if you create a linked list. It's not hard to apply in-place method. Connect the select nodes instead of creating new nodes to fill the new links in. In-place method. Well, we can just loop through the next one, keep k pointers, and connect the nodes. It's not that difficult. Optimize to by priority queue. Wow, you see for the first one, for the solution here, we just loop through use linear time to find the smallest one, but with a priority queue, we can improve it to log k. So the idea is simple. Yeah, O log k. The idea is very simple, but for JavaScript, there's no priority queue, so it's a little tricky. I suggest we talk to the interviewer to say that suppose there is a priority queue. I might do separate videos about how to implement priority queuing in JavaScript. Well, remember, rather than we loop through all the nodes, all the k nodes to compare, we could maintain a tree, which always puts the smallest one at the top of the to the root of the tree. So that's a basic priority queue. Now, when we are looping through the next one, it will cost a linear time. When we are pull the smallest one, it costs us linear time. So it's basically linear time. Okay, and then merge this one by one. Well, we can merge the top two. We can merge these two together. It will cost us how compare. Yeah, it's a linear time and then linear time. Okay, yeah, use the number this. So linear. Wait a minute. Merge them together. 2 sorted list. Oh, linear time. Yeah. Some of the merge process. Us. Yeah, I made a mistake. There's a merge process. And we get OKN. Wait a minute. Merge these two. It will cost us OKN. Yeah, n divided by k. Oh no, here. N divided by k. And then we merge them. It will cost us 2. And then we need to merge another one. This is a kn. Well, oh yeah, yes. So these nodes like is used in this merge, and in this merge, and then in this merge. So it's basically for each node it will be used for k times. Cool. The last one. Rather than if we are doing the one by one, like merge the big list to make a longer list and merge then merge these the longer one with this one, we maybe want to merge them shortly first, like merge these two and merge the rest two and then merge that rest two. Something like this is separate them pairs, this pair, this pair, this pair, and then merge these 3 and then merge this 2, merge this one. Well, since this is the divide and conquer method, it will be improved because let's see our code. We first create a merge to list. A merge to list is it's simple. We keep 2 pointers and keep the result, right? Keep a false start, and then compare these two. We keep appending the smaller one to the P, right? If it's smaller, we set the P to it and move P1 next. And while this is done, of course there might be some nodes left, so we append them. So we return the final list. And then what we can do, we can, in my solution, we merge them from the start, merge the first one and the last one. So I kept 2 pointers, start, end, merge these two, and then you see end. Choose the end. For every end, we'll start from the start, right? So for this one, I merge this one to the first, and then merge this to the first, merge to 1, to the merge 3 to 2, and then every time we choose from after this round is end. Okay, wait. For the first round, end will the loop will ends when start is bigger than end, right? Start and bigger than end, which means end here, start here. Or they are the same, right? If they are the same, we don't merge. So the last element will be start. So yeah, end minus 1. If they are the same, start equals to end. And will keep end actually will be at the right end, right? All the nodes are already merged. All nodes to the right are merged. So end, we don't need to change the end. And if the start is overflow is bigger than end, it means end is still right at the end. So and we don't need to touch the end. So the idea is merge 5. Okay, pick 5, merge to 0. Pick 4, merge to 1. Pick 3, merge to 2. And now what do? We need to pick 2, right? Actually, the 2 exists. So we become pick 2, merge to 0, pick 1, and pick 1 is actually equal to 0. So we do nothing, and now we will go again, move 1 to 0. So finally we get the result. Return the list 0 or null. Cool. So that's for this one. Divide and conquer. The 2, 3, 8 product array except self. Give a nums output is equal to the product of all the elements except itself. Well, I can use first. We can get the product of all the elements and do the division. Yeah, this is called linear time. Naive solution would be, yeah, it's get the product of all the other elements. What it costs us quadratic time and one space. What is it? And we can cache the result. Yes, means the product from left and product from right. It will cost us linear time. Result. What finally I did is we get the result, and for this is actually what it did here. Product from left from right. But actually, we don't need to actually keep these two array, right? Product from left, product from right. This means when we get the product from the left, we can actually get the result in the second loop to get the product from right. We can merge these two into one. So you see, we get the product, right? And we set the result, and then we go backward and update the result. So yeah, we can use only one array. Originally, we used three arrays, and now we only use one. But this one is a result, so it's not mandatory, so it should not be counted as a space complexity. Well, this one is simple. Integer to English words. Well, this is a very trivial one. Not tedious one. We need to convert a non-negative integer to its English word representation. 123, 45. There's no and, right? 123, 1,234,560. Well, the key point is to do by segments. Choose do it 3 by 3, right? First, a transform. If the 0 is special case, we return it. We transform into string and collect the result array because we have a maximum. So we get the basis. The basis is for the 67. There's no something like million, like thousand, so it's empty. And we got thousand and million and billion. And there are some words, right? Words for one digit, 1, 2, 3, 4, 5, 6, 8, 9. And there will be two digits have a set different word, right? So 20, 30, 40. Why we have this empty? This is 20, 30, 40. Why there's empty? Well, let's continue. There's some special one. It's 10, 11, 12, 13. Why this is special? Now we create a buffer. The buffer means to handle this segment by segment. We flush. When we flush, we will get what? We will get the base, right? Get the base and put the base into the buffer, and put the buffer into result. So the base, this one, the unit, will be handled in every 3 digits. So we loop through the string backward and multiply by 3. If it's 0, we need to flush the buffer. We flush the buffer, and if it is 1, if previous one is 1, we handle the special case, special num I minus 1 plus num I. nums I minus 1. Yeah, so like 91 nums I, if this is 1, so okay, this is a special case. The previous one is 1. We handle the special case and then go to the next one. If it is not 1, and if it is bigger than 0, then we push the word 0, num I. Word 0, the first one. If 1 digit, they're I, right? If num I is 0, this is 90. '91. Suppose this 91. This is 90. I see. So if it's 2 digits 90, there's nothing. Okay, so we set it, and then if it is 1, it means this the second one be here. If it's bigger than 0, we push the words in. This is always 91 or 67, right? So we push this one and push the words 1. Wow. I'll just skip down this question. I think it's very tedious. We need to just handle the boundary very well. It's labeled as hard. The general idea doesn't change. We just use a buffer. Do it segment by segment by 3. If its mod is 0, it's not actually this digit. It's actually the what? It should be this one, right? It should be this one because we use this divided by I. First one is 0, so this one and 0, 1, 2, 3. This. So we only flush at here. Okay, and if there's a 2, so it means this one. So it's 500. So buffer push 100, and then buffer push the word, right? Yeah. And then finally flush, and finally we reverse and join. Well, we doing it in pop, push and pop, because shift and shift is slow. Okay, that's all for this one. And then we have this merge intervals. Collect the intervals, merge all overlapping intervals. Well, if we draw these intervals, and we will see, first I think we should sort them, right? Yeah, we sort, and then we just merge them one by one. Well, we check if 2 intervals is overlap. If it is, we will this is the intervals. We slice these 2 out and merge them and push them back. Well, this I'm not suggesting we use this. We can create a new array and we merge them. We merge them and put them in a new array. We need to do inline. There isn't any better solutions. Connected components. Time is n log n, and then we merge them. How can we merge? Merge is like this. So it's linear time. It's a constant time, except this one. Sorting, yeah. I think we're doing the sort thing. Cool. Space. We use no gun. We can do in place. We don't need more than constant additional space. Yeah. If you use array, we use linear time space. If not, we're doing like this. But this actually splice and merge in splice is not it's not linear time, remember. So I say we sort it in the backward and then we merge backward, so we can only use pop, right? We only use pop. Yeah, shift is not okay, I think. I did a mistake here. Remember, we only do pop and the push. It's better. No. The in place, if I push, it's still, there's a problem, right? Ah, I see. We don't need to pop the elements, actually. We could just, I know what happened. Yeah. We could, like we get the 1, 2, 3, 4. We could just set, like we merge this 1 and 2, merge into 1. We could just keep a track of the current position and merge it to like 1 here. But this one is new one, like say new 1. 2 is still 2. Now we merge 3 and 4. 3 and 4. So we merge it, and the 3 and 4 is still there. And we just have this as new 3, something like this, right? So we actually, this is a constant time. Cool. Subarray sum equals to k. This is we have mentioned a lot of times. Subarray of these elements actually could be do the sum subtraction, like the subarray of 1 here could be actually sum till this one and subtract sum to this one. So we do just with near time to cache the sum and do the subtraction, right? Here's this is the space, so linear time and space. Accumulated sum. Yeah, space time. Cool. Next permutation. One, 2, 3, 1, 3, 2, 3, 2, 1, and 1, 2, 3, 2, 1 to 1, 2, 3. Well, it's kind of a difficult analysis here. So the solution is very simple. If you analyze if suppose there is no next permutation, it will be totally descending, right? So the condition for we can get the next permutation is next permutation is actually we need to make it bigger. Next permutations. 1, 2, 3. Next one is 1, 3, 2. Next to greater permutations, right? 3, 2, 1. Next one is 1, 2, 3. If not such range is not possible, we means to rearrange it as the lowest order. So this is a special case. We just reverse them. So for 1, 1, 5, actually we got 1, 1, 5, 1. If we think of this problem as like a line graph, we will notice that we can only find a valid except the special case. Next permutation exists when there is a turning point, right? It's like go down first and go up. So the solution it's pretty straightforward. We first, from right to left, find the first descending slope. Get bottom next to pick xy. From right to left, find the first number bigger than x. Swap it, and then we sort numbers from right to right, y. You see, so the rightmost pick means the biggest one from right? First biggest one. So we do from right to left and initialize it to the first one, and if we found the if we found that it is bigger than the previous one, it means go down a little bit, then it's the first pick. We break. So this is the first pick. Like 1, 2, 3 here. Like let's suppose we have 1, 2, 4, 3. The first pick was before, right? So we first go up and go down. So the 4 is the first pick. And now we find the first number bigger than the bottom number and the swap with the bottom number. If no bottom, skip. Okay, so if the most right pick is not 0, so this is the special case. If we find the rightmost pick, and then we will go right, we will search from right again, and this will loop through all the way to the 0, and try to find a number that is bigger than the number next to, just right before the pick, like this number. So we need to find a number just right bigger than this one, and then swap it like this. We're going to find it to 1, 3, 4, 2. And then say j to rightmost pick, so j here, and k equals the last one. And then if j is smaller than k, we swap it, swap j and k. J will move. Okay, so we will change 1, 2, 3. Suppose this is 1. Oh, suppose it's okay. 1. This is 10. Okay, we first find the pick and find the first number which is bigger than 2 and swap it. This becomes this, right? And then we will do what? We will swap k, j, and k. So we will swap 4 with 1. So 1, 3, 1, 2, 4. Not 1, it's 10. 10. So the idea is simple, like because we are finding the first right pick. For each number, there will be no number bigger than it from behind, right? So the first number, which could have a number bigger than it, will be the number just before the pick, which is 2. So we found this 2. This is the target we need to swap, and go right from left, and we find it because it's right next to pick. The rest numbers will be in descending order. So we swap it and swap to this one. It's still in descending order, right? Because this is the first number bigger than it. So the rest number is still smaller than it, and this one is bigger than it, and this will be in descending order. So we need to reverse it. So we got this. Yeah, and this is a special case. Special case that if the first pick is 0 here, we don't do anything, and we just reverse it. So this will help us. So yeah, find the first pick from right. Okay, this is 31. K closest point to the origin. Okay, so this video actually goes up to more than half an hour. I think I'll stop at K close point. So this will be 8. I'll stop at 10. Okay, so this is a series of videos about 10 problems in a video. Okay, so K close point to the origin. We have a list of points. Find the K closest to 0. Okay. Well, because we're going to get k. Well, first we can just get all the distance and sort, right? Well, this costs a lot of time. We don't need that. So actually, we could use a priority queue and get the distance for each node and put the distance in the priority queue, and the priority queue will be at the maximum k. This is the priority queue. Well, in a real interview, I think we don't need to implement this. It's kind of long. We just suppose there's a priority queue. Okay. Well, the idea is simple. We create a hash map. Why do we need a hash map? Oh, get the point, right? Get the distance. Okay, so these actually the points and we put the points in the priority queue, but we need to actually get the distance, right? So we use a hash map to map the priority queue to the distances, and then for each point we get the distance and use priority queue to add the point, right? And we get the priority queue size. If it is oversized, we pull the this is what is it? The priority queue, the order is A, B, get B, A. So it's actually descending order, the maximum. The farthest node will be put at the top of the priority queue. So we pull, we would remove the farthest. So this will actually, each add will cost log k, and the pull will cost log k. Yes, it's log k and log kn. This is what we can do. This priority queue. Divide and conquer. Sort. Yeah, this is n log n, but actually we can improve to n log k. Divide and conquer. Wow, this seems simple. But worst case is n squared. Okay, I'll use priority queue. K something would be almost, I think most of them are priority queue. Minimum removal to make valid parenthesis. This typical valid parenthesis problem. Let's see what I did. So invalid minimum removal. I use a stack to keep track of the invalid the invalid parenthesis. If the left, we push it. If right, we get it. If they match it, we pushed. We get the right. Not only the character, but we'll push the index. So if it is empty, we push it. If it is left, we do nothing. We pop it, do nothing. And if not, we push, right? We push the rightmost, and then push the new one. So it's actually will be a stack of the invalid parentheses. The parentheses in the stack are all invalid. If there's nothing, if it's empty, we just return. Now we collect the result, all right? How we do that? Collect the valid string with 2 pointers. This is abandoned. The result, okay, start from 0. We will loop through all the stack, and the result will push. If it's 0, we will slice the first invalid one. Well, it means that before it was valid, right? We slice it, and then if it's not 0, we will slice the previous one, right? Okay. Just slice them up and collect them. So we are going to return the valid string. If we are going to determine if they are valid or not, or determine the count, we maybe don't need to use the stack. We just do a count, right? It's an integer to track the count. But we need to get exactly where the invalid parenthesis occurs so that we can collect the right valid string out, extract the valid string. So we use a stack and push both the invalid characters and the index in. Cool. So this is linear time, and this we use a slice, but actually each character will be actually traverse maximum once, so it's still linear time space. We use a stack, so worst case is linear, so linear. Wow, it's very long. Linear. Wow. So I think okay. I'll stop looking. Okay, minimum parenthesis. This is the 3, 3, 3. Okay, the last one, serialized and deserialized binary tree. Okay, I need to serialize the following tree: 1, 2, 3, 0, 5, 4, 5. This is the 1, 2, 3. This is the BFS, right? Yeah, I think. Okay, this is serialized. This is okay. The result, we walk. If null, we push it. If not null, we push the value in and then walk left and right. So it's not BFS, but 1, 2, 3, 4 null 5. 1, 2, 3 null 5. I think we're having different one, right? We have a DFS, like 1, 2, 3. We collect it first and walk to the left, and then collect it first and then walk. So I have a pre-order traversal. Let's take a look. 1, 2, 3, no, 4, 5. Is this right, man? 1, 2, 3, 2, 3, 4, 5. Oh, okay. One, 2, 3. Oh. So what happens if there's a 6? Yeah, 1, 2, 3, 4, 6, no 5. 6, 5 is before 6 is before 5. Expected output 3, 4, 5. 3, 4, 6. 4, 5, 6. 4, 5, 6. So it's actually BFF, right? Well, we see deserialize. Deserialize, serialize it. Actually, I think we have a different serialized thing. You see, we're actually using different format. Yeah, you see, we have a different one. It's not this. We are using pre-order traversal. 1 to null 3, 4, 6 null 5 null. Yeah. This is we use a recursion to do it. Now we need to deserialize it. The deserializes we first because we got array, we parse into array. We just empty or null, we do nothing. We build, we still use recursion to build. We get the first item. If it is not null, if it's null, we return null. If not, we need to create a tree node. Because it's pre-order, we met something, we build it, right? We met 1, we build, and then we make it 2, and then we build. So we make next one is right, return node. So the the representation in array form actually is a full tree. So even this 2 will have 2 null nodes. So every node, if it is null, the next nodes are always be this left child and right child. So we use this build. This build will actually create a node every time. Create a node. So the shift is not very good. I think we should reverse it and do pop. It will be faster. Okay, so every time we build a node, and it will be called recursively. So this build is done. It's recursion. I think I will do serialize and deserialize video in tomorrow. Okay, this is 297, 297, 297. So this is the first 10 problems, right? Okay, so that's all. See you soon. Bye bye.